So this video is, as obviously titled, about finding the inverse of a matrix. And the idea is that we have some matrix A, and the inverse is going to be denoted as A with a little -1 sign. So that does not mean 1 over A. That means A inverse, just like we have F inverse or sine inverse, things like that. This is A inverse. And basically the definition of the inverse, the inverse of a matrix, is denoted, as I mentioned before, with that little A inverse symbol, and has the property that A multiplied by A inverse is equal to the identity matrix, which we call this big I. And it's also the same if I did it the other way around. Okay, and you might wonder, why do I have to check this? Why do I have to check both directions? Because if you remember in the last video, we found out that multiplying by matrices in different directions will give you different answers. So it is important that we check that this goes both ways. The identity matrix, and just as a refresher, remember the identity matrix, if A and A inverse are like 2 by 2 matrices, then the 2 by 2 identity would just be this. The 3 by 3 identity matrix is when you have basically just that perfect RAF form like so. These are the matrix equivalent of the number 1. And so that's just kind of something that maybe you can hold on to. And so to find the inverse, right, how do we do this? Well, there's a couple things that we're going to need. So the first thing is, right, there's a condition. And that condition is that the inverse only exists for square matrices. And what do we mean by that? So we mean by like n by n matrices. So before we kind of cover the why of, we can only do this for square matrices, which will be something we covered in the next video, I'm just going to, kind of go about in this video how to actually find the inverse of a matrix. So for 2 by 2 matrices, okay, so for the inverse of a 2 by 2, so the 2 by 2 inverse is not too bad. There's like a small little formula for it. So given our matrix A, and let's say that A consists of like A, B, C, and D here, okay, then the inverse of this turns out to be 1 over the determinant of A, which is just a number. Remember, that's just a number. And then all we're going to do here is we're going to swap the A and the D. So we're going to do D and A, and then we're going to put negatives in front of the B and the C, and that is what it is. Now, the reason why this is what it is, you can evaluate this kind of a long way. For now, I'm going to say, hey, we have a little formula. You can use this formula. That's how you come up with the inverse of a matrix. So when might this be useful? So for example, if I say, let's solve the system, 3x1 plus 4x2 is equal to 3, and 5x1 plus 6x2 is equal to 7. We can write this in the matrix equation form as 3, 4, 5, 6. We have our x1, x2 here. And on the right side, of course, we have our 3 and our 7 vector. And remember that in this matrix equation form, this is A, this is the vector x, and this is our solution vector B. And the idea is that if I were, so let's write down everything. So this is a 2 by 2, this is a 2 by 1, this is a 2 by 1. And the idea here is that if I were to multiply the left side of this equation by A inverse, right, What happens when you multiply A inverse and A? Well, according to this, it just becomes the identity matrix, which for all intents and purposes is just the number 1. And so the identity matrix times X, this thing becomes the identity, and then the identity times X is just going to be the vector X. And so the left side, we just get X equals. And on the right side, I also have to multiply on the left side by A inverse. You might be like, well, why? Why don't I just multiply it on the right side? Well, two things. Number one, because order matters, right? If I multiply on the left side by a matrix, I have to do it on both sides, because if I multiply one side on the left and one side on the right, we may get something completely different. But then also, remember that B is a 2 by 1, and if I try multiplying that by a 2 by 2, it's not going to work. So on the right side, the solution we very quickly get is A inverse times this B vector. So let's figure it out. Let's use our newfound formula. So over here, the first thing I'm going to calculate is the determinant. So the determinant of this matrix 3, 4, 5, 6, the determinant, is going to be 18 minus 20, which is negative 2. So 1 over the determinant is going to equal negative 1/2. So we'll kind of tuck that away. And so the inverse matrix is going to be negative 1/2 multiplied. All right, so we swap the 3 and the 6. So we get a 6 here, a 3 here, a negative 4 here, and a negative 5 here. And we multiply this together. So we're going to get not a very nice matrix, but we'll get negative 3, 2, 5 halves, and then negative 3 halves. And this is the inverse. We could check this, right? It's not too hard to check this. If I were to multiply it by this matrix, what should I get out? I should get a box of 1, 0, 0, 1. So in fact, let's do it. Let's just check, like, even though we're supposed to check both sides, let's just check one side just for the sake of having done an example. So 3, 4, 5, 6 multiplied on the right side by negative 3, 2, 5 halves, and negative 3 halves. Right, what do we get? Okay, so if we do the first row times the first column, we're going to get negative 9, and then 4 times 5 over 2 is 20 over 2, that's 10. So we'll have negative 9 plus 10, so that's going to give us a 1 here. Then the next up, we have the first row, second column, so we get 6 for the first one, and then 4 times negative 3 halves is a negative 6, so that's 0. 5 times negative 3 is negative 15. 6 times 5 halves is 30 over 2, which is positive 15, so we get a 0. And last but not least, we're going to get 5 times 2 is 10. And then 6 times negative 3 over 2 is negative 18 over 2, which is a negative 9. And last time I checked, 10 minus 9 is 1. So it looks like this is promising. So to finish solving this, this little matrix equation, without having to do any row reduction or anything like that, we simply multiply both sides of this equation by the inverse. We're going to multiply it on the left-hand side. So on the left side, we're going to get just x. And on the right-hand side, we're going to get this matrix negative 3, 2, 5 halves, and negative 3 halves. And multiply this by 3, 7. And so what do we get for our solution here? We're going to get negative 9 plus 14, which is 5. And then we're going to get 5 halves times 3, which is 15 halves, minus 21 halves. 15 minus 21 is negative 6. So negative 6 halves, which is negative 3. And fantastic, and we're done. This is going to be our solution vector x. Great. Now, in all practicality, right, this is kind of like a long, tedious way of doing this, because we know we can just pop this into an augmented matrix form, RREF it, and solve it. And that is what we would do if we had a 3x3 or a 4x4 or a 5x5 or whatever. So it turns out this is like an efficient thing to do for 2x2 matrices, not really so much to do for a 3x3 or larger matrix, but it's just to show you that if you ever had something like AX equals B, you can manipulate this thing. So, you know, it does come with the requirement that A is an n by n matrix, but we could manipulate it by multiplying both sides by the inverse and then kind of continuing onward. So we have a little bit of a restriction, but as long as we meet that restriction, then we can kind of introduce this new tool. And the inverse shows up a lot, as you're going to see in the next video. It kind of has some massive implications with it. But if you think about the inverse as the ability to go backwards, right, as a transformation, the inverse is doing this, right? So if we're in our domain, right, if we're in our domain and we have our codomain over here, and maybe we have the range of some transformation inside of it, right, the range, and we have some vectors b over here, right, some different vectors, so b1, b2, b3, and we have some, input vectors x1, x2, x3 over here. The idea is that the inverse takes us this way, right? The inverse transformation will take us back the other way. And hopefully you remember that from pre-calculus, right? If I wanted to show that an inverse exists, there are some conditions that our function had to have. Namely, our function had to be 1-to-1. Our function had to be onto, right? We could only have an inverse if it passed like the vertical line test. And the vertical line test was basically making sure that we were onto, things like that. So just something to keep in mind as we kind of continue with this video. The rest of this video is just going to be showing you how to calculate like the inverse of a general matrix, like a 3x3 or larger. And then the theory stuff is going to come back in the next video. But just something for you to kind of keep in mind while we're doing this. Okay, so the last thing that I'm going to show you here is how to find the inverse of a 3x3 matrix. Now the process for doing this is listed out in the textbook on page 140, or rather the proof for it is. But I'm going to try and very loosely hand wave some reasoning over it. So it turns out that if you have some matrix A, what you can do is you can pop that matrix A, you can put it inside of another matrix, if you will, and you can line it up right next to the identity matrix here. And the idea is that if we can row reduce the matrix A to itself be the identity matrix, okay, if we can row reduce this to be the identity, and we do the same exact operations, whatever we're doing on the left side, we do them on the right side to the identity matrix. The idea is that A inverse will pop out over here, okay? Which, maybe it should kind of make sense. Maybe it doesn't make perfect sense. I'm just going to leave it there that if we do the row reduction operations on the left side to the matrix A and we get the identity, then on the right side, if we do those same operations to the identity matrix, that's going to give us A inverse. And the idea is that if I smush A and A inverse together, those operations would cancel out and give us the identity. Again, the proof is on page 140. It's chapter 2.2 in the inverse of a matrix section. You can check it out. But I think that the best thing for us to do is just going to be to try and solve one of these. So let's, by example, find the inverse if it exists. Find the inverse of A equals, let's say 0, 1, 2, 1, 0, 3, 4, -3, 8. Okay. Now you notice I said, find the inverse if it exists. Just like with functions, not every function has an inverse, or rather the things that don't have inverse aren't functions, right? Like if we have a sideways parabola like this, x equals y squared, there is no inverse, things like that. We have to pass a vertical line test. So, just because A represents some sort of transformation doesn't necessarily mean that it has an inverse. So the idea is that if I can row reduce this sucker to be the identity matrix, then it will have an inverse. The reasons why this all happens, I'm going to explain very thoroughly in the next video. So if you want, you can pause this video and bounce to the next video and start watching some of the theory and then kind of come back. But if you just want to see how do you do it, we're going to do that right now. So as I mentioned before, we're going to start by popping A into this giant, massive, augmented matrix of sorts over here. It's 1, 0, 3, 4, -3, 8. And on the other side of this augmented matrix, I'm going to put the identity. So 1, 0, 0. And I'm also, picking the identity that matches the size of the matrix that we are, of course, going to work with. And the idea here is I'm going to row reduce on the left side. I want to get row reduced echelon form. That's the goal. So what could I do first? I'm probably going to swap row 1 and row 2. So my row 1 is going to swap and become row 2. My row 2 is going to be what my old row 1 is. And then I'm going to kind of jump a couple steps. So I know that because there's a 1 here and a 4 here, that if I multiply, say, row 1 or our old row 2, we'll say, by -4, and I add it to row 3. So if I take, and I want to replace my row 3, so I'm going to take -4 of my current row 2. I want to add it to row 3. That's going to get us a 0 in that first spot. So if we do all of this at once, okay, if I do all of this at once to the entire matrix, right? So we got to do everything at once. Okay, so if I replace my row 3, so I multiply by 4 and I add, let's see what we get. Or -4, excuse me, and we add, let's see what we get. So -4 and add is going to give me a 0 here. That's still going to give me a -3 here. And then I'll have -12 plus 8, which is -4 here. Now, what do I get on the other side? Well, I still get a 0 here, but now -4 times 1 over here and adding to row 3 is going to give me -4, and then I have a 1 here. Okay, so that's the third row, and then all I did for the other ones is I swapped. So 1, 0, 3, 0, 1, 0, and then 0, 1, 2, 1, 0, 0. Okay, so that got me that matrix. So now we continue. So there's one pivot in the right place. There's another one. So the next thing we have to do is what? Simplify row 3. So I'm going to replace row 3 now. And I'm going to do it by taking 3 of my row 2. I'm going to add it to row 3. So make another augmented matrix. And we crank it out. So the first row stays the same. 1, 0, 3, 0, 1, 0, 0, 1, 2. The second row is also staying the same. 1, 0, 0. Third row, not so much. But if I do 3 and add, we're going to get 0 here. 6 and -4 is going to be a positive 2. And then I'm going to get a 3 here, a -4 here, and a 1 over here. And we're almost done. We almost have this thing in RAF. So let's get a 1 here, and to do that, that's going to be to replace row 3 by multiplying it by 1/2, so 1/2 of the existing row 3. So if we do that, so again, the first 2 rows stay the same, 1, 0, 3. 0, I guess I kind of like when I had different colors, so 0, 1, 0. This is going to be 1, 0, 0, and 0, 1, 2. But what happens to row 3 now? So we get 0, 0, 1, and then we get 3 halves. We got fractions. 3 halves, -2, and 1/2. Fractions are a-okay to have, right? Normally, it's actually much more realistic to have fractions than whole numbers the entire time. Okay, so our last thing we need to do is to get rid of those numbers and turn them into zeros. So the last operations we have up to bat is we can do this a myriad of ways, but let's replace row 2 by multiplying row 3 by -2, row 3, and then adding it to row 2. And then let's replace row 1 by taking -3 row 3 and adding it to row 1. So let's see what we get. So the third row is going to stay the same, 0, 0, 1. And we have 3 halves, -2, and 1/2. So now if we kind of mosey on to row 2. Okay, so row 2, we're supposed to be taking -2 times row 3 and adding it to row 2. So that we should get the identity matrix over here no matter what if we're doing these operations, because -2 times row 3 and adding it here is going to give me a 0, and multiplying -3 by row 3 and adding it here is going to give me a 0. So we're really interested in just what happens on the right hand side. So if I multiply row 3 by -2 and I add it to row 2, what do I get? So I'm going to get, multiplying by -2 here is going to give me a -3, plus 1 is going to give me a -2 in this slot. If I multiply this by -2 and I add it to row 2, I'm going to get a +4. And then if I multiply this by -2 and I add it to row 2, I'm going to get a -1. And we kind of mosey on to finish. So if I do the same thing for row 3, but this time by -3, if I multiply 3/2 by -3, I'm going to get -9/2. If I add that to row 1, I'm just going to get -9/2. If I multiply this by -3, I get a +6, and I add it to row 1, I get a 7 up here. And if I multiply that by -3, I'm going to get -3/2 in that first slot. And so when it's all said and done, what we have here on the left-hand side, this is the identity matrix. Now on the right-hand side, we have what I have just kind of claimed is the inverse matrix. And this is the process. This is how you do it if you want to find the inverse of a 3x3 or a 4x4 or however large a matrix is. You go through this RAF process. Very careful, but obviously our matrices are a lot bigger now. And I encourage you to pause the video and actually make sure that this thing is the inverse of what we started with by multiplying it on both the left-hand side and then trying it on the right-hand side, and just making sure that you do indeed get the identity matrix in both instances. But that's going to do it for this video. The next video is going to be very, very theory-based. It's going to be tying together why can we only do this with square matrices. It's going to be relating things like linear independence and solving, the matrix equation AX equals 0 and linear transformations and a whole bunch of things. We're going to start tying things together. So the next video is arguably probably the most important video in the entire class, or one of the most important videos in the entire class. So make sure that you're ready to go and you don't really have very many questions kind of going into it.